All right, folks, so today we're looking at our reciprocal trigonometric functions. We're looking at their bases, assuming there are no transformations. Now, and I think I was able to pause that recording before the dog started barking. But we can build these reciprocal trigonometric functions in the same way that we built reciprocal polynomial functions earlier in the course. So we'll take our discoveries from earlier in the course and we'll just apply them here. So number one, if we find any roots in our denominator, they're going to tell us locations of vertical asymptotes in our reciprocal. Okay, so that means if I have 1 over the sine of x, and so I look at the sine of x right here, that's my denominator, and I'm looking for any roots of my denominator. Okay, well, there's going to be a root here, there's going to be a root there, and in fact, there's going to be a root at every single addition of pi there furthermore. So these tell us already the locations of some vertical asymptotes for the cosecant of x given by 1 over the sine of x. So I'm working right here. Okay, so I would have a vertical asymptote at x equals 0. I would have a vertical asymptote at x equals pi right here. And I would have a vertical asymptote at x equals 2 pi right here. So in fact, my vertical asymptotes are where x is equal to 0, pi, 2 pi, etc., 3 pi, 4 pi, 5 pi. Now you'll notice that goes on forever in this direction, but our vertical asymptotes also go on forever in that direction. So I would expect a vertical asymptote where x is equal to negative 2 pi, negative 5 pi, negative 11 pi, any integer multiplied by pi. Fantastic. That's our first rule. Well done. Now we're looking, okay, so we'll look where we have any vertical asymptotes in our denominator, then we're going to have roots in our reciprocal. Our sine function has no vertical asymptotes. So our reciprocal will have no roots. Fantastic. That's an easy rule for us right now. Okay, now where y is equal to plus or minus 1 on our denominator, oops, and that's missing there, on our denominator, then our reciprocal will also have y equals plus or minus 1. We call these, if you remember, we call these invariant points. Good, so, all right, well, y is equal to plus 1 here in our denominator. It's equal to minus 1 right there. So at those locations, then we're expecting our reciprocal function to also share those points. All right, locations of local maximums will tell us, of the denominator, will tell us locations of local minimums in the reciprocal function. So that means, where I was looking right here, where y happens to equal plus 1, this is also a maximum of my of my denominator. And if it's a maximum of my denominator, I'm expecting this to be a minimum of my numerator. Down here, this is a minimum of my sine function, so I'm expecting this to be a maximum of my cosecant function. Fantastic. And lastly, I'm looking, okay, so wherever my denominator is positive, my reciprocal will also be positive. Wherever my denominator is negative, my reciprocal will also be negative. So we can use this logic to build our functions right here. We know that we're going to need to find the behavior of our function around our asymptotes. So at this, say, vertical asymptote, then my function will either need to approach positive infinity or negative infinity. And I can look at this and I can say, well, hang on. Looking at rule 5 right here, where my denominator is positive, the reciprocal will also be positive. I know my denominator is positive for this entire interval. So I'm not able to approach negative infinity with my reciprocal. I must be approaching positive infinity. And I can use that same logic to say, okay, those are my behaviors around the vertical asymptotes. Now I need to sketch the general shape inside. Well, I know I have a minimum right there. I should be looking at something that looks like this. Fantastic. Over here, I have a maximum. That's in between two vertical asymptotes. So my behavior right here must look something like this, using the same logic as before. Fantastic. And in fact, your cosecant function is simply alternating. They almost look parabolic in shape. They're not exactly parabolic in shape, but it's alternating this shape that opens up, and then it opens down, and then it will open up, and then it will open down forever and ever and ever. Fantastic. Now, if I am listing my invariant points right here, I can do so. My minimum, okay, so my invariant points, I have one at pi over 2, 1, and I have one at 3 pi over 2, 3 pi over 2, -1. And then this pattern will repeat. So then at 5 pi over 2, I'll have one at +1, etc. I'll put ... right there, and maybe ... dots beforehand to represent that this pattern would have continued on in the other direction as well. Fantastic. So we're doing darn well so far. Trying to lighten everything up. There we go. Our local maximums and minimums. Those will occur at x is equal to pi over 2, 3 pi over 2, 5 pi over 2, etc. on forever in that direction and in the direction beforehand. Fantastic. So we can use that same logic to try and come up with the general shape of our secant function. That is the reciprocal of our cosine function. I'll encourage you, maybe pause the video and try and follow through the logic right in here. And if you're feeling a little bit stuck, instead of going forward and seeing what the answer is, go back, see the logic we used finding the shape of our cosecant function, because you'll be using the same logic down here with your secant function, just the locations of these features will be a little bit different. You should be able to handle this one, frankly, on your own. So what I'm going to do is I'll ask you pause the video, figure that one out, and then come back and you'll be able to see the answers here. Good, so we should be able to see the same general shape popping up right here, just translated over pi over 2 units to the left or to the right, or yeah. So if we're working right here, then we should, I'm hoping, feel relatively comfortable with this general shape. I'm hoping we were able to follow the same logic. We were able to find our vertical asymptotes using the same logic. We're able to recognize there are going to be no roots of our secant function using the same logic. We're able to recognize our invariant points and our local maximums and minimums using the same logic. You'll notice in here I've labeled the minimum, maximum, minimum. Obviously what I've been labeling is the behavior of the points on my reciprocal function, not on the cosine function itself. Fantastic. Whoops, and it looks like, you know what, looks like there's an x missing up there. I think it will show up on yours just fine, but mine has it missing. So we fixed that. Nice work, us. Lastly is our cotangent function. So I have the tangent function sketched in here. We haven't explored it in our own lessons yet, but you were asked for homework the one night to go explore your tangent function on Desmo. So I will assume you're relatively comfortable with this function. So if we're working in here, and you know what, I'll try and choose a color that will show up well. We'll try a nice bright pink. Does that, yeah, it contrasts enough. So we're working here, our cotangent function, it's 1 over the tangent function. All right, if that's the case, then we're going to have vertical asymptotes wherever our tangent function has a root, just like before. Fantastic. So I have a vertical asymptote here, and here, and here. I can plot those, nice and easy. Good, these vertical asymptotes are at x equals 0, x equals pi, x equals 2 pi. That's enough to see the pattern. Our vertical asymptotes are going to be wherever x is equal to ... Don't forget that ... ahead of time. 0, pi, 2 pi, etc. Fantastic. Okay, now we're going to have x-intercepts. Hang on, none of our other reciprocal functions had x-intercepts. So let's go check again. Where do we have x-intercepts? We're going to have these x-intercepts, these roots of our reciprocal, wherever there are vertical asymptotes in the denominator. So we're going to want to go find any vertical asymptotes that were showing up in the denominator, and I'll use a red color in here, and I can see that there's a vertical asymptote right in here. I can see there's a vertical asymptote right in here, right? And these are x is equal to 3 pi over 2, and x is equal to pi over 2. So I'm going to expect to have roots in my reciprocal function at these two locations. So my x-intercepts are where x is equal to ... pi over 2, 3 pi over 2, that's enough of a pattern, 5 pi over 2, etc. Alrighty, now our invariant points, remember, our invariant points come wherever x is equal to, wherever y is equal to plus or minus 1 on our base function. So I'm looking here and I can see, okay, well, here's 1, there's negative 1, I can just look across, okay, here, 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 and here. There, so I found 4 invariant points. I could label those. I don't need to list all of them. Perhaps I will. We're working here. You know what? I'll say pause the video and label them on your own, then come back. Good, so we see here, we're working at pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. That's enough of a pattern for us, and they alternate. The first invariant point is at positive 1, the next one at negative 1, the next positive 1, the next negative 1. Now, I'll emphasize again, I called this the first invariant point. Really, there's nothing significant about this invariant point, right? The invariant points continued off in the direction towards negative infinity as well. So it's not like that really is the first invariant point. It's just the first one that we plotted here. So using this logic here, okay, so we have invariant points. We don't have any local maximums or minimums on our base function, the tangent of x, so we're not expecting any local maximums or minimums on our reciprocal, the cotangent of x. And if that's the case, then that means there are no turning points, right? So if I'm looking right in here, all right, then I need to check, okay, here I have a vertical asymptote, and I need to check, is my function going to approach this vertical asymptote as my function approaches this vertical asymptote from the right? Is my function going to approach positive infinity or negative infinity? And I know if my function is positive, if my base function is positive, if the tangent of x is positive here, then my reciprocal function will also be positive. So I look and I see, okay, well, hang on, my function is absolutely positive here. So I'll have to be working up towards positive infinity. And I'll use that same logic. Remember, only the pink vertical asymptotes in here are the ones that we're using for a reciprocal function. The other ones were vertical asymptotes that we found on our base function, right? So then I need to look, okay, as I approach this vertical asymptote from the left, am I going to be approaching positive infinity or negative infinity? Well, I see that my base function is negative down here, so my function will be approaching negative infinity. So this general shape that I'm looking at over here goes through the invariant point, goes through the root, goes through the invariant point, and then heads off towards negative infinity. All right, and then I can keep going forward. I can use the same logic. I'll encourage you to use the same logic on this region. Try it out. And we should be looking at something like this. Again, the same general shape. And in fact, your cotangent function is this same general shape plotted over and over and over again, off towards negative infinity and off towards positive infinity. So that should be enough, folks. I know it's a nice and short lesson for today. You should be able to handle the practice problems for section 6.5 at this point. Nice work.